Now the CNH point group has a single proper axis of rotation and a horizontal mirror plane. Now since we can perform a rotation followed by reflection through a plane perpendicular to the axis of rotation, the CN axis is necessarily an SN axis as well. And so the group CNH has the following unique elements: an identity, Cn through Cn to the power of n minus 1, reflection through a horizontal plane, Cn followed by reflection through the horizontal plane, and so on through Cn to the power of n minus 1, followed by reflection through the horizontal plane. And so the order of the CNH point group is 2 times n. Now the S sub n point group has a single improper axis of rotation, and so the group contains the elements the identity, S sub n through S sub n to the power of n minus 1, so that the order of the SN point group is n. Now notice that S sub 1 contains the elements the identity and a mirror plane, the plane of the molecule, and so this is the same as the CS point group. S sub 2 contains 2 elements, the identity and an inversion center, and so this is the same as the C sub I point group. Further, if n is odd, then S sub n is the same as C sub nh. So for the S sub n point group, n is an even integer that is greater than or equal to 4. Now there are 3 point groups of the dihedral class. And these are denoted D sub n, D sub nh, and D sub nd. And these point groups are characterized by having one primary axis of rotation, C sub n, and n C2 axes, which are perpendicular to the primary axis of rotation. So for the D sub n point group, we have the identity, a Cn axis, and n C2 axes perpendicular to the Cn axis. And so the D sub n point group contains the identity, C sub n through C sub n to the power of n minus 1, and n C2 axes, so that the order of the D sub n group is 2n. Now the D sub NH point group has a primary axis of rotation in C2 axes perpendicular to the CN axis and in vertical planes. Now some of these vertical planes may be a dihedral plane, but the element which distinguishes the D sub NH point group is a horizontal mirror plane. Now because we can perform a rotation followed by a reflection through a plane perpendicular to that axis, we also have an SN axis. So the distinct elements of the D sub NH point group can be represented as follows. Identity, C sub n through C sub n to the power of n minus 1, n reflections through vertical planes, a horizontal mirror plane, n rotations by 180 degrees, and S sub n through S sub n to the power of n minus 1. So that the order of the D sub NH point group is 4 times n. Now the D sub ND point group has a primary axis of rotation in C2 axes, in dihedral mirror planes, and an S sub 2n axis. So the unique elements of the D sub ND point group can be represented as follows. Identity, C sub n through C sub n to the power of n minus 1, in C2 rotations, and n reflections through dihedral mirror planes, and S sub 2n to the power of m, where m is an odd integer ranging from 1 to 2n minus 1, so that the order of the D sub ND point group is 4 times n. Notice that the D sub ND point group does not contain a horizontal mirror plane. So given distinguishing characteristics of the point groups, we can construct a decision table, or in this case a flowchart, that will help us assign molecules to point groups. So the first determination that we make is whether or not a molecule belongs to one of the special groups of either high or low symmetry. These molecules are generally easy to recognize. If the molecule does not belong to one of the special groups of either low or high symmetry, we next find the principal axis of rotation. Next, we determine whether or not the molecule has a C2 axis perpendicular to the primary axis of rotation. If it does, then there are n C2 axes perpendicular to the primary axis of rotation, and the molecule belongs to the dihedral class of point groups. And if it does not, then the molecule belongs to the cyclic class of point groups. Now, once we determine that a molecule belongs to the dihedral class of point groups, we next check to see whether or not the molecule has a horizontal mirror plane. If it does, then the molecule belongs to the DNH point group. If it does not, then we check to see whether or not the molecule has a dihedral mirror plane. If it does, then the molecule belongs to the D sub ND point group. And if it does not, then the molecule belongs to the D sub N point group. And once we have determined that a molecule belongs to the cyclic class of point groups, we next check to see whether or not the molecule has a horizontal mirror plane. If it does, then the molecule belongs to the C sub NH point group, and if it does not, we check to see whether or not the molecule has a vertical mirror plane. If it does, then the molecule belongs to the C sub NV point group, and if it does not, we check to see whether or not the molecule has an improper axis of rotation. If it does, then the molecule belongs to the S sub N point group, and if it does not, then the molecule belongs to the C sub N point group. So let's look at some examples, and we'll start with water molecule. Now, the water molecule does not belong to one of the special groups of either high or low symmetry. The principal axis of rotation is a C2 axis. Now, the water molecule does not have a C2 axis that is perpendicular to this principal axis. And so the water molecule belongs to the cyclic class of point groups. Now, the plane of the molecule itself is a vertical plane, and we also have the vertical plane that is perpendicular to the plane of the page, which passes through the center of the molecule. And so there are two vertical mirror planes. And so the water molecule belongs to the C2V point group. So next we'll look at the boron trifluoride molecule. This molecule does not belong to one of the special groups of either high or low symmetry. The principal axis of rotation is the axis that is perpendicular to the plane of the page passing through the boron atom and is a C3 axis. Now, this molecule does have C2 axes, which are perpendicular to the C3 axis, and there are 3 of those. And so the molecule belongs to the dihedral class of point groups. Now, the plane of the molecule is a horizontal plane. And so boron trifluoride belongs to the D3H point group. So next we'll look at the benzene molecule. Now, benzene does not belong to one of the special groups of either high or low symmetry. The principal axis of rotation is the axis that is perpendicular to the plane of the page and passing through the center of the molecule, and that is a C6 axis. The molecule does possess C2 axes. There are 6 C2 axes. That are perpendicular to the C6 axis, and so this molecule also belongs to the dihedral class of point groups. The plane of the molecule itself is a horizontal plane, and so the benzene molecule belongs to the D6H point group. So as an exercise, assign the xenon tetrafluoride molecule to a point group. Now, I will also add a link to a very good website that is supported by the National Science Foundation, where you can get as much practice as you like assigning molecules and ions to point groups. Now, as a second exercise, construct the Cayley table for the C2V point group. And as a third exercise, show that a tetrahedral geometry does not imply tetrahedral symmetry. That is, show that a molecule may have a tetrahedral geometry, but does not belong to the tetrahedral point group. Okay, so we will end here for today. Next time, we will look at some of the applications of point groups, and then we'll move on to matrices. So I hope you have enjoyed the 6th lecture. Thanks for watching.